That's not something you cut off. No.需要用到一些IP 啊，16 Oh, I see.
还可以往这上面。以前那个结果你忘记了，可以再写。
2 more minutes. All right. Thank you. It's like this expansion. It's not
That's just my way of smoothing and making it easy.
how should I pronounce?
I mean, the Spanish pronunciation is Alvaro. You can pronounce it.
All right, yeah, good afternoon, everyone. Yeah, today is a great pleasure to have DARPA Co-Manager Alvaro Velasquez. I just learned the pronunciation correctly. So yeah, so Alvaro is a program manager in the Innovation Information Office, I2O of the DARPA. And so he currently leads the programs on neurosymbolic AI. So before that, Alvaro oversaw the machine intelligence portfolio of investment for the AFRL in Rome. So Alvaro received his PhD degree in computer science from University of Central Florida in 2018. And he's a recipient of the Distinguished Paper Award from AAAI, Desk Paper and Patent Award from AFRL, and the National Science Foundation Graduate Research Fellowship Program, NSF GRFP Award, and the University of Central Florida 30 Under 30 Award. So he has authored over 60 papers and 2 patents and served as the associate editor of the IEEE Transaction on Artificial Intelligence. So without further ado, let's welcome Dr. Velasquez.
Yeah, thank you for the introduction and thank you for the whole university for the invitation. It's been great to be here. What I want to present today, I titled it an exploratory talk because I'm hoping to elicit discussions as to what a concerted investment in foundation models should look like. So for those of you who don't know, DARPA invests in defense relevant research. And so when we talk about foundation models, probably a lot of you think about, ChatGPT and all these really cool LLMs. And the question is, how can we come up with similar successive or sequential decision making? And I'm going to go over what the challenges are, some potential opportunities. And I want you to keep in the back of your head, what the right problem space should be that we should be investing in. In particular, the private sector is going to look at this, no doubt. Amazon is looking at foundation models for robotics. Google is looking at foundation models for navigation. So we would have to make an argument as to what won't the private sector look at that we should nevertheless be focusing on. So keep that question in the back of your head as I go through this presentation. Right, so this is a high-level outline. I'm going to discuss what foundation models look like, in particular the LLM version of foundation models, some of the architectural considerations and how those perhaps might change when we try to do sequential decision-making. The technical underpinnings, once you have your architecture, typically this is trained in a self-supervised manner over highly diverse data. It's much easier to do with language than it is to do with sequential decision-making. How do you fine-tune for downstream tasks, right? We usually train over all this data, but then we want to fine-tune to a very specific type of problems that we have, whether it's with text generation or a dialogue agent or whatever the case is. One of the unique things that OpenAI added to Instruct GPT and GPT 3.5 was the reinforcement learning from human feedback. So I'll cover how that works. We'll discuss what it means to bring in actual action choice within these models. These things are typically trained using next word prediction, which is a fantastic way of training things. It's a very sort of frequent learning signal that you can leverage. But as soon as we add an action choice of an embodied agent acting out in the world, a lot of the underlying assumptions that make this method work for ChatGPT sort of ceases to work for sequential decision-making. Then I'll talk about scoping the problem down. As I mentioned, some folks are looking specifically at robotics. Some are looking specifically at navigation. What should we be looking at as the academic and funding communities? I'll do a little bit of a deep dive in some of my own research on neurosymbolic transfer learning, which I think can be used for this sort of fine-tuning problem. And then we'll talk about some potential avenues that would be interesting for DARPA. And again, part of the purpose of this talk is for you people to tell me that's a stupid idea, that's a good idea, this is where we should be looking at. And so I really hope that we can get some kind of discussion going on this front. Right, so at a glance, what is a foundation model? Foundation model, some large architecture usually built on top of a transformer architecture, or at least attention mechanisms that form the core of transformer architectures. They're trained on highly diverse data, and they're fine-tuned for downstream tests. So here you see, for example, question answering, sentiment analysis, information extraction. And really the evolution of foundation models sort of stems from transformer. This is a paper probably a lot of you have read, Attention is All You Need, from back in 2017. This is a very, very powerful architecture that OpenAI then leveraged for all of their GPT models. GPT brought in the self-supervised training, brought in the fine-tuning for downstream tasks, brought in the reinforcement learning from human feedback, and I'll briefly cover what all of those advancements look like. But first, I wanted to show this because I thought this was really cool. So this is from a YouTube lecture. If you look up Sparks of AGI on YouTube, this was an invited lecture at MIT where Sebastian Bubek, he's at Microsoft Research. Of course, as you may know, Microsoft has invested in ChatGPT, so they have early access to GPT-4, which is supposed to be this really cool multimodal foundation model. And so he asked ChatGPT and GPT-4 to generate a proof of the infinitude of primes such that every line rhymes. And if you see ChatGPT, it gives you what seems like a correct proof, but it clearly doesn't rhyme. But then you read the GPT-4, it says, yes, I think I can, though it might take a clever plan. I'll start by noting Euclid's proof, which shows that primes aren't just aloof. Assume we have a finite list of primes and that none have been missed. Multiply them all together and add one just to be clever. It doesn't just rhyme, it has the kind of structure you would expect in a poem, and it is a correct proof of the infinitude of primes. So this is tremendously impressive. And it almost gives the illusion that these things have, well, general intelligence, that they can reason, that they can plan about things. But broadly speaking, they can't really plan. And there are a lot of counterexamples, and this is where the autonomy comes in. When I say foundation models for autonomy, I mean sequential decision-making. I mean areas like reinforcement learning, planning, the kinds of agents that can solve games, that can drive cars. So this goes beyond just language and vision. Now, in that lecture, they reference some paper that says that a general intelligence should be able to reason, plan, solve problems, think abstractly, comprehend complex ideas, learn quickly, learn from experience. Sort of very vague claims. Sebastian Bubeck thinks it can do all of these except plan. I'm inclined to agree with him. And so that is the question. How can we get these things to plan in an embodied agent acting out in the real world? In particular, when you think about sequential decision-making, you typically reason about some kind of decision process. This is the mathematical formalism that captures the space of potential actions the agent can take, right? So in the example of Deep Racer, which is a simple kind of 3D car racing sim, you have state spaces, which are sort of your field of vision, the location of your car, that kind of thing. You have actions, which in the case of Deep Racer are very simple. You either go at 1 meter per second, 2 meters per second, turn 15 degrees, turn 30 degrees. Your transition dynamics that tell you if I'm in a given state and I take a given action, what is my probability over the next states? And either a reward or a cost function that is a proxy for what you're trying to solve. In the case of Deep Racer, this is trivial. Get to you have to stay within the lanes and get to the end of the map as quickly as possible. So we figure out a way to come up with a reward mechanism that satisfies those demands. The most obvious one is you penalize the agent the longer it takes to get to the end of the map, and then you give it a very high reward when it gets to the end of the map. And so given this formalism for a decision process, you generally just want to find this mapping of states to action, your decision-making policy, such that whenever you observe a state, it tells you the optimal action to take. You observe feedback from your environment, and you keep this going. That's sequential decision-making in a nutshell. There are a lot of assumptions baked into this, and we can discuss what those are in terms of Markovian assumptions, whether it suffices to just have my current observation to make the optimal decision. So whether your state space is fully observable or partially observable, there are all kinds of little idiosyncrasies to different domains. So that's something else to keep in mind as we try to think of what a foundation model for autonomy looks like. Is it too complex to start with partial observability? Should we have full observability? Is it too complex to start with history-dependent dynamics, i.e. non-Markovianity? Or should we start with Markovian dynamics, et cetera, et cetera? And part of the challenge with these foundation models is that unlike in language, where you have a sort of universal modality, right? In language, when we say, let's train over highly diverse data, well, it all still looks like language. Whether it's Wikipedia or a novel, it follows some semblance of the same syntax and semantics. So it's diverse data, but grounded in a universal form. However, when we think about sequential decision-making, this assumption goes out the window. Because in the previous case, I gave you Deep Racer, and now I have some other environment that's part of this diverse data set that might be a high fidelity autonomous driving simulator like Carla. Then your state space looks dramatically different. Your action space looks dramatically different. You have a continuum of how much you turn a wheel, how much force you put on the brake, on the gas, and the rewards look dramatically different. In particular here, you not only want to get to the destination as quickly as possible, but you want to obey the laws of traffic. And so your reward signal looks very different. So basically we have the state, action, transition, and reward signals are all factors of variation when we think about training a foundation model over highly diverse data. Right, so now we get to what the architecture looks like for foundation models currently. They're all built on top of some flavor of attention network. Sometimes it's a full transformer, sometimes it's only the encoder part, sometimes it's only the decoder part. But for the purposes of this talk, let's just say it's a transformer. It leverages attention. What is attention? Attention is actually, at a high level, it's a very simple mechanism. If you think about database retrieval, you have a database with a bunch of values. You have a query of the values that you want to retrieve from your database. So you compare the query with the key corresponding to each value. When you have a match between your query and your key, you retrieve the corresponding value. Very simple. All attention does is give you a vector for your queries, your keys, and your values, and those vectors are learnable. And that's the gist of it. Now, of course, if you want to get into the details, there are extra things on top. You generally have an encoder that transforms your text into tokens. You generally have a decoder that transforms it back. But really the key technical insight is that machine learning version of database retrieval. And if you look up this paper, it has like 70,000 citations. So this is, very highly regarded paper. And so that what you get out of that is that if you, for example, want to translate a sentence to another language, you might imagine that each word in the sentence is a token. And what it means to perform this query key comparison is to look at all subsets of combinations of words to see which are more aligned with your objective, whether that's text generation, whether that's translation, et cetera, et cetera. Now, this is very powerful. I'm a big fan of transformers, but I have no reason to believe that this is a natural platform for sequential decision making. So if you think about in the reinforcement learning community, we tend to jump on the bandwagon of the latest, greatest architecture in their respective domains, right? When convolutional neural networks came out and they were destroying all the computer vision benchmarks in 2011, 2012, the year after deep Q networks came out, taking the convolutional neural networks to play Atari, right? When the transformer architecture came out, then a couple years later, the decision transformer came out, which tried to do the same. It tried to reduce reinforcement learning to sequence modeling so that we could use these architectures. I think one of the interesting questions to ask is, what is a natural platform for sequential decision making? Such that you take into account what I explained earlier. There's a feedback mechanism from your environment, right? And it needs to be, in some sense, very data efficient. If you want an embodied agent acting out in the world and fine-tuning based on real-time data, this needs to be extremely data efficient, and transformers are not. Right, so once you've figured out the architecture of a foundation model, the next step is to train it using self-supervision. Self-supervision, broadly speaking, is you have unlabeled data, but you can find a way to provide a label based on the context of the task you want to solve. What does that mean in the case of language? We actually have massive shortcuts we can take when it comes to self-supervision here. Because if you take Wikipedia and you just start removing words and you train the agent to predict what those words were, that's a form of self-supervision. It sounds trivial, but it's very powerful and there's text all over the place. So this is partly why these LLMs work so well. The self-supervision isn't, I don't want to undermine their results, but it's an easier problem when it comes to language. In vision, we actually also have some very interesting approaches for self-supervision. Here I've put contrastive learning. Contrastive learning basically tries to learn a representation. If you take a mini batch of images and you want to learn the dog in this case, the dog becomes the anchor. We perform a bunch of perturbations to the dog, rotate it, change the colors, whatever, and we call those positive samples. We take everything else in the mini batch, we call them negative samples. We feed the dog through a discriminative classifier, usually a ResNet model. We feed the positive and negative samples to a separate ResNet model. We train based on something called a contrastive loss. And what the first ResNet model is learning is a representation that's close to the dog manifold, but far away from all the other manifolds. And this is an area that has blown up tremendously in the past, three years. So we have these very nice shortcuts we can take in language and vision, but it's not clear what this kind of self-supervision looks like for sequential decision-making. And there are methods for self-supervised reinforcement learning, but they don't accomplish anywhere near what these methods can do. So to me, that's still very much an open question. So once you have your architecture, once you figured out a way to do self-supervised training, which is I can't overstate this enough. It's a very big investment. So it could potentially cost hundreds of millions of dollars to train a very large model using these self-supervised methods, which is why when you see these very large systems, it's typically OpenAI, DeepMind. This has been the case, since at least 2013, as far as I can remember. So it's important for people like us to leverage their investments. But anyway, once you have your architecture, once you've figured out a way to train it in a self-supervised manner, you take that from OpenAI and you say, I want to apply it to my task. I have my data set, I have the things I want to solve. And so that's where the fine tuning for downstream tasks comes in. In the case of language, again, we have big shortcuts we can take. So here I have an example of something called chain of thought prompting, where you can take the outputs of your large language model, let's say for answering questions. So the question here is, Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? Of course, the answer is 11. But if you say 11, it doesn't do much for the agent to have enough learning signals to know what you're really trying to get at. These systems are actually very bad at math. But if you tell it a chain of thought of how you arrive at 11, you say, well, he started with 5 balls, 2 times 3 is 6, 5 plus 6 is 11, the answer is 11. The agent can actually learn and generalize to more broad, similar mathematical questions. It's the simplest thing in the world to fine-tune these large language models for your test. In the case of computer vision, of course, you have conventional transfer learning. If you pre-trained your vision model on ImageNet and you wanted to detect some kind of new data that is perhaps classified and you have very little data, well, you train it on ImageNet, you freeze all the earlier layers, and you fine-tune the last layer or the last few layers on your sensitive data, and that's how you can fine-tune for downstream tasks. So again, sort of the theme here is that in language and vision, we have all these nice shortcuts. What does this mean in sequential decision making? Again, it's not clear. Finally, this is sort of a tweak that if you read the ChatGPT paper they threw in there to make their InstructGPT even better. Again, fairly straightforward stuff. They hired 40 contractors. They had them in a supervised way fine-tune the model. They just asked ChatGPT to generate queries. The queries are good. You use it for fine-tuning. And then this part, these 2 columns, are the reinforcement learning from human feedback. This is like the big deal that they brought in. They gave ChatGPT a prompt and asked to give 10 different answers, let's say. The human rank orders those answers based on how good they were. You use that to train a neural network that is a reward model. So it learns to predict, if I give you an answer, how good is it? That's the whole prediction. Once you have that, you can just keep fine-tuning ChatGPT using reinforcement learning as your training technique. And that's how they get the results. That plus a tremendous amount of compute, and I don't know, is it 1 trillion parameters in GPT-4? Something like that. So that's really what you're seeing here, is tremendous amount of computer resources. And I want to make it clear, even though this is trained using reinforcement learning, that is not sequential decision-making. You're not observing feedback from your environment. And that is exactly what we want. So how do we do all of that? How do we take these highly diverse data sets that, again, in the context of sequential decision-making can look like, 3D Racer, Grand Theft Auto, Grid World, and I forgot what this is, but like a 3D object manipulation environment. Clearly, the state spaces, action spaces, transition dynamics, reward signals are all different here. So how do you train a foundation model based on that and have it and act with an external entity, for example, the real world or some other agent, receive feedback and be able to adapt in terms of that feedback? And there's a very good survey paper I highly recommend, Foundation Models for Decision-Making. This shows like all the early work in this space. Now, as I mentioned, there is some early work that has adapted these technical underpinnings that make up foundation models i.e. the transformer, they've applied it to RL. So this is the original decision transformer paper. They basically take a very large offline data set of experience. Well, it can be Atari games, it can be whatever reinforcement learning setting you want. But they give a very, very nice example. Let's say you want to do reinforcement learning for finding the shortest path in a graph. It's a stupid idea because we have very good fast algorithms for finding shortest paths, but for the sake of illustration, let's say we have a training data set that's all random walks. So a lot of these are very, very bad. They're not anywhere close to the shortest path. What the transformer can do is focus on the sub-policies of each graph and compose them into a shortest path. And again, this goes back to the attention mechanism. It can look at the subsets of edges that most correspond to having a short path and pick and choose from different sentences, which in this case would be random walks, to make a policy. Now that's all well and good, and reducing, reward state actions into a kind of language and translating that into an optimal sequences of actions is a very good idea. But why this doesn't suffice for a foundation model is that you are not observing feedback from your environment. There's no sequential decision making. You've taken a large offline data set. You don't collect new data. It's an offline data set. So if the world is changing, how are you going to adapt to that? The Gatto paper, this is by, I want to say DeepMind. They take it a step further. They also use a transformer architecture, but they try to be a little more general. They say we're going to take all kinds of domains. We're going to take Atari, we're going to take robotic manipulation, all kinds of games. And using the same weights for the transformer, we're going to solve all of these games. And the way they do it is by, at the end of the decoder, they mask certain actions that would not be valid actions. So their action space is the union of all action spaces of everything they trained on, and then they just mask it so it doesn't make invalid actions. They have very good results, but again, you're not obtaining feedback from your environment. This is an offline approach. And so that's my main criticism when you try to take sequential decision-making and reduce it to sequence modeling, is that you don't actually have this feedback mechanism, which is, for an embodied agent, is the whole point. This is some recent work from UC Berkeley and Google, where they've tried to reduce this problem to the scope of just robotic navigation. And again, this is one of the questions I have. What is the right scope for the investments we should be making? Robotic navigation makes a lot of sense, because if you want to create a foundation model that can generalize across many different robots, navigation would be a very neat domain, because you can represent all the objectives as the goal image of where you want the robot to be. Maybe you want to get from here to that door, so you show it a picture of that door. So the goal is the same for all robots. The sequence of waypoints by which you get there as a high-level planner is almost the same. And so all they have to do is use an embodiment context to capture the idiosyncrasies of, is my agent taller than the other agent? All these little perturbations in the field of vision. And then they use something called a shared action abstraction. What does that mean? For all of these robots, in some sense, you can use the same action space. You just have to scale it based on the size of the robot, the maximum speed of the robot, and things like that. So you can reasonably train a foundation model for this kind of context. Now, you have to consider, what are the factors of variation here, right? We're not going from Atari to flying an aircraft, right? These are all very similar state spaces. The observations are more or less the same. The action spaces they're assuming are more or less the same. So that's why this works as well as it does. So I want to talk about some of my work, sort of changing gears here, on one thing we might leverage also as a shared abstraction. So in the previous method, they had a shared abstraction for actions. I'm going to present some work on shared abstractions for the goal of the agent, such that if two environments share the same goal, we can fine-tune, we can transfer information to the target environment. The key insight here is that if you have a goal, if you state it as a natural language objective. Here we have a simple Minecraft goal. It says, if the agent observes wood, it must eventually visit a factory to make a tool. And the agent must build at least 3 tools and then go to the home tile to build a house. So if you've looked at Minecraft grid worlds and things like that, this is a fairly standard objective. Now you can transform this into a linear temporal logic formula. Here G means globally, F means eventually. And we have ways to translate this into a deterministic finite automata. So now we have a structured representation of the objective. And a DFA is simply a state transition system where you have an initial state, an accepting state, and some logical conditions that tell you when you can transition between states. If you make it from the initial state to the accepting state, you satisfied your objective. So the question I was asking there is, how can we take this and use it to transfer knowledge between 2 environments that look different, but have the same logical objective? And so for my purposes, I only looked at the weakest languages of all, which are regular languages. They can be represented by these DFAs. But really, if you want to get fancy, there are all kinds of structures as you go up the Chomsky hierarchy. You know, if you want to define a context-free language as your objective, you have push-down automata. Context-sensitive languages, you have linear bounded automata that can represent it. And recursively enumerable languages can be represented as a Turing machine. So there's a lot of depth and richness to what you can do with these kinds of structures. And you can even learn these structures. So these are some papers we published last year in ICAPS, where we looked at the problem where you don't actually fully know your objective. You just have an agent acting out in the world, and at some point it receives a signal that something positive happened. You might imagine even in a simple game of chess, if I told you the reward signal for chess, I beat you, I get a +1, you beat me, I get a -1. If you have enough time, the agent will learn a really good policy, but it takes a lot of moves to actually win the game of chess in this way. You need intermediate guidance. And so what you can try to do is you can try to learn these DFAs, even for games like chess. Maybe it turns out that if my opponent's rook is in a certain position and my knight is in a certain position, this is a good tactic. And so you can actually learn these kinds of tactics in a DFA structure and then provide intermediate rewards based on that structure. And so you'll learn much more quickly. So that's what we were exploring. We took some guidance from the L-star algorithm. This is sort of the classic grammatical inference algorithm from the 80s for how you learn regular languages. And so I'll very quickly cover that. So the L-star algorithm assumes that you have an oracle. The oracle knows the language you're trying to learn. And so you go up to the oracle and you say, is this sentence in my language? And a sentence in this context could be rook is here, knight is here. A sentence is just a sequence of meaningful events. Doesn't have to be language. So you ask the oracle, is this sentence in my language? Will this help me win at chess? The oracle says yes or no. Eventually, you ask it enough of these questions that you can build a hypothesis DFA. And you go to the oracle and you ask, is this my language? Did I figure it out? If the oracle says yes, you're done. You figured out chess. If the oracle says no, it gives you a counterexample. It says, you're missing this sentence, right? So it gives you a counterexample in the symmetric difference of the 2 languages. And so with that, you can ask more questions and eventually you converge. It's a very nice algorithm. But historically, who is the oracle? This is a practical dilemma, right? If I want to apply this in a real setting, well, who is this all-knowing oracle? In the case of reinforcement learning, it's the reward signal. Again, if you're playing chess, your oracle is if you achieve the reward or not. So what we did is we actually mapped reinforcement learning in this paper and planning in this paper and used the reward signal to learn these intermediate tactics. And then what we did is we learned the expected value of all the transitions in that DFA. Based on that expected value, we can more frequently reward the agent and they learn much more quickly. And the expected reward is akin to saying, how often was this event, knight in this position, rook in this position, how often did that lead to me winning the game? It's a very simple empirical expected value. But the nice thing is, if you have two environments that perhaps look very different, but they share that same objective as a DFA, we might say, well, can we learn in this environment, learn the empirical expected values of that DFA, and then distill that into the target environment? They look different, but perhaps the rocks here are the green squares there, perhaps the table here is the blue square there. And so basically that gives you a way of doing transfer learning. So that's the fine tuning for downstream tasks without having to have the same state space, action space, transition dynamics. All it assumes is that you have the same reward signal that can be represented as this nice structured representation. And then there are a lot of things you can do there. You can distill those empirical expected values into the reward signal of the agent in the target environment, into the loss function if they're using something like a policy network, or into the action value function if you're just doing old school Q-learning tabular based approaches. And so we compared this to a DeepMind baseline. This is back when DeepMind's AlphaZero was sort of in vogue and everyone liked AlphaZero. Here the orange curve is AlphaZero trained directly on a 25 by 25 Minecraft-like environment. The blue curve is an approach we came up with that is Monte Carlo tree search extended with these DFAs, trained directly on the 25 by 25 environment. And the green curve is this transfer learning I just explained, where we first learn on a 10 by 10 environment and only transfer those expected values of the DFA. We didn't transfer any parameters of the neural network, nothing like that. And we still obtained a very significant increase in the win rate. Then we tried something else. Then we tried a different flavor of transfer learning. So this is known as curriculum learning, which is where you have an agent, they want to solve a complex task. So the natural question is, can I decompose that task into a set of simpler tasks? How do I sequence those tasks? And how do I transfer knowledge from one task to another? And here we again use this DFA representation to answer all of those questions. Here we looked at something called an object-oriented Markov decision process. This is basically like the decision process I mentioned earlier. It's just a state space, an action space, how you transition, what your rewards are. But now it's augmented to have classes and parameters. So you can have objects that belong to the class of trees, and the parameters might be that there are between 1 and 3 trees in the environment, and they can only be in these locations. So it's a simple way to parameterize MDPs, which is good for transfer learning, because ideally, if you can solve this particular map, you should be able to solve any map that has the same objective. And so we applied our approach on a bunch of domains, a bunch of grid worlds, some robotic manipulation environments, and we obtained state-of-the-art results compared to other curriculum learning baselines. And this was accepted for publication in ICAPS 2023, so it's not actually out yet, but if anyone wants the paper, I'm happy to share. And the goal is that by leveraging these kinds of, the goal for the fine-tuning part of foundation models is that by leveraging these symbolic abstractions like the DFA that I mentioned, that we can make up for the drastic changes in the environment, that we can go from something like Deep Racer, which is very abstract for driving, to Grand Theft Auto, to perhaps even a real autonomous driving. Right. So now, as far as considerations for DARPA, this is where I think I need the most help. This is the question of, well, why won't the private sector do it? Why won't Amazon do it? Why won't Tesla do it? I'm not sure. So I'm trying to figure out what the answer is. Perhaps one direction would be safety critical systems. No one should be applying these things to safety critical systems, but sometimes in the Department of Defense and some other areas, you may not have a choice. So which is why I think the private sector wouldn't look at it. I mean, as cool as this would be for something like an autonomous driving system, which you might consider safety critical, it's out there in the roads, it can hurt people. There's no reason why Tesla would actually look at this. I mean, the liabilities are tremendous. Here I simply mentioned, this is a paper we just had accepted as well. If, I'm happy to share it if anybody's interested. Where we looked at the outputs of ChatGPT, we translated it into an abstract form that can be formally verified. And if it fails verification, we take the counterexample to fine tune the ChatGPT model to make it, in a sense, more trustworthy, more likely to satisfy the specifications we want it to satisfy. And in this context, trust can come in many forms, right? Trust is a very overloaded word. Trust can mean transparency, explainability, verifiability, whether you can get a human to trust it, even if it's not good. It means many different things. Should that be what we should focus on for this investment? You guys can tell me what you think. Another interesting area is if you consider an embodied foundation model subject to constraints on the size, weight, and power. This is known as SWAP. In the circuit design community, we very often use these terms. In the AI community, not as much. But I think this is important because in the DoD context, we don't know where we might deploy these things. They might not be close to a power source. If you want to deploy one of these things out in Mars to explore Mars, it's clearly not going to be close to a power source. But when you think about what the private sector might do, in my naive mind, I imagine something like this: a house robot, you charge it every night. There's no real restrictions on the kind of power that it must consume. So I think this might be another interesting direction to start a new program on foundation models. So to conclude, of course, foundation models, for example, ChatGPT, they've achieved tremendous success. They generally are underpinned by 4 key factors: the architectural design, again, typically some kind of transformer or attention-based architecture; the self-supervised pre-training, which again is very expensive, requires a ton of parameters; the fine-tuning to downstream tasks. And for our purposes, if we want to do sequential decision-making, the integration of some kind of feedback signal. So I mentioned some of the challenges to all of these. All these are easier for language and vision, but presumably much harder for sequential decision-making. One of the key insights, I think, is that we have to find the right shared abstractions. In the case of language is kind of its own universal abstraction. It's its own common modality across diverse data sets. In the case of sequential decision-making, as I showed, that's not the case. So how do we come up with the right shared state abstraction, action abstraction? I showed some of my early work as to what a reward abstraction might look like using these DFAs. And finally, and perhaps most importantly, again, what should DARPA be investing in that private sector may not be properly incentivized to explore? As I mentioned, this might be safety critical systems, integrating trust in some form or another. It might be low SWAP foundation models. It might be both, or it might be something I haven't thought of that maybe you fine folks have given more thought to. So with that, I thank you for your time. I open the floor to questions.
So, very interesting talk. I was sort of thinking about some of the things that you mentioned regarding what DARPA should be investing in. And clearly, I think safety is a very important part of what DARPA's investments should go in.
Mhm.
I think if you look at a number of research progress that has taken place, for example, on constrained RL, oftentimes these constraints tend to be expected values, right? So not it doesn't give you a lot of confidence in terms of the constraints that are needed in safety critical systems like self-driving. And so I think a big open question here is, how do you handle hard constraints? How do you handle hard constraints when decisions need to be made based on uncertainties? So like a POMDP type of an RL.
Yeah.
So I think these are clearly areas where I think DARPA should be focusing on, where perhaps the industry might not. But another area which I think the industry may not be incentivized to sort of spend their money on are distributed implementations of machine learning. So and I think the military, for example, would be very interested
Yeah.
in those. So, you know, why would, let's say, you know, a Facebook or Microsoft or Google be that critically interested in distributed ML when their advantage over us is precisely the enormous computing power that they have, right? And I think that's an area where I believe, you know, DARPA may want to think about investing as well.
Right. And that has a natural embodiment in another area that the DoD is interested in more broadly, which is Edge AI.
Right.
So in Edge AI, I recently went to a conference for this, where we were trying to figure out what investments we should be making in Edge AI. So in Edge AI, you have this distributed computing and distributed learning. But when you look at what the private sector does, they assume that you have this cloud infrastructure. And of course, they want to sell you a cloud infrastructure and they make a lot of money. But in the case of the Department of Defense, where we might deploy these things, very frequently, you don't have access to a cloud. It's what is known as a restricted or denied communication setting. So there are all kinds of interesting challenges pop up because now you don't have this general purpose cloud that can learn anything that is not constrained by power. Now you have these smaller edge devices that have to do everything, which ties back to the sort of low swap idea. Yeah, I think that would be a good one, the distributed angle. Yeah.
I mean, regarding Edge AI, I don't know if you're aware, but we have an AI institute at Ohio State, which
Yes.
whose focus is on Edge AI.
And I'm meeting someone from that institute later, right?
Yeah.
It is, okay, I was gonna ask, I didn't wanna.
But don't you want to, you know, you get part of, you know, folks who are part of the institute.
Oh, I see, yeah.
Yeah.
Looking forward to it.
Yeah, so looking forward to chatting.
Sure.
Yeah, just to complement that, you know, I do think your reaction that Edge AI is related to low swap is kind of spot on. I think at one level, if you don't solve the low swap problem, you look at extreme distribution as a surrogate for, you know, the centralized learning of these foundation models. And that blows up, that you've only made a hard problem harder.
Yeah.
So you've got to simultaneously look at ways of sort of shrinking the learning in that process. And, you know, part of my interest comes from thinking about that from the perspective of how knowledge guides can help in producing low swap. So if you think about it, even in the brain, we learn something inefficiently, but we are able to shrink that into something that's equally effective when we have more context or more abstraction that's guiding, you know, how you can represent that. So I think that sort of knowledge guided as a basis for creating smaller machines is probably.
It's interesting that you bring that up. So I'm co-organizing a neurosymbolic computing workshop in August. And the theme of that workshop is what does that neurosymbolic computation look like at the edge so that you can minimize the number of parameters, because these symbolic structures, which the knowledge guidance can take on the form of a symbolic structure, whether you call that a rule base or in the case that I presented a DFA, whatever form that takes, it can drastically reduce the number of parameters, because we're not going to take a foundation model, you know, they're in the hundreds of billions of parameters. You're not going to fit that on a low swap device. That's just too energy intensive. But with the right symbolic structures, you drastically reduce the number of parameters. So we see this, for example, in my work on reinforcement learning. When you have the DFA, it's a form of knowledge that makes it so the neural network doesn't have to internally capture the dependencies of all these transitions in the DFA. So you can actually get away with much smaller policy networks. I think that's a phenomenon that would carry over broadly to other domains as well. Yeah. So I agree with you on that. And you're invited to the workshop if you want to come.
When is this?
Seattle in August. Yeah.
Actually, one thought, so maybe that's also something the industry may not care. So it's the data. So in this, so I think in many of the DoD scenarios, maybe you don't have. So let's say you use LLM for decision making, sequential decision making. maybe just the nature of it, it's hard to collect data compared to language, where you can just grab the whole internet to.
Right.
Yeah, so maybe that's something DARPA.
Do you think, what form do you think that would take? Do you think that would be a synthetic data generation or making things so incredibly data efficient that what we have out there would suffice?
Yeah, I don't have good answers right now, but I feel like that might be an interesting direction, where the industry may not care, but it would be important for DARPA also.
That's true. Well, there is something with industry as well. If we go back to the case of autonomous driving. Again, this would be a terrible idea if Tesla tries to do something like this, but if they wanted to, they have the resources to develop the ultimate simulator for autonomous driving. They could spend years developing, they can invest hundreds of millions of dollars. In the case of the DoD, we don't have that. We take these sort of more abstract models and then try to make that carry over to the real world. And it just doesn't work. So we do face that more significant data problem hurdle in the DoD.
Yeah, so I guess following up Kevin's idea in the small sample world. I guess the meta learning, continual learning, this type of learning structures that help us to be able to do the large pre-training, but be able to fine tune with just a small number of samples. I mean, in the end, you could have encountered some of the environments that you have never seen, and whether or not we will be able to fine tune with very small set of samples to such an environment turns out to be very important.
Yeah, I agree. I mean, and meta reinforcement learning, few shot learning, curriculum learning, there are all these flavors of transfer learning when it comes to reinforcement learning that I think we need to draw on that knowledge for definitely for the fine tuning. I have to think more about the self-supervision, but there might be something there. Yeah.
Yes. Yeah, actually, there have been ideas like meta self-supervised learning.
Oh, okay.
Yeah, that can leverage, the pre-trained model and then fine tune in some in some of the task specific cases.
All right, that meta self-supervised learning, interesting. Yeah, thanks for the lead on that.
You have some thoughts on the adversarial side of reinforcement learning, which wasn't covered in your talk, but I guess would also be of interest to DARPA, which is you train it in a simulated environment or something, but when you deploy it in actual world, there may be adversarial elements that are.
That's true. There is
you
a
need to recognize and then figure out how.
there is a more natural dedicated adversary in the DoD context than in other contexts. Because in other contexts, you have an adversary in some sense, but it's the world itself. It's your uncertainty of the world.
Yeah.
It's not actually an intelligent adversary. So yeah, I think that would be a good angle too.
Yeah, I guess another aspect I would like to bring up, maybe it's not something DARPA may be interested, but I mean, since a lot of people in academia, we are interested in explaining why this large language model works, and especially from a principled way or from theoretical foundations. So I mean, I would suggest that DARPA to think about this fundamental theoretical research.
I wonder why you say that. No, I think, but that's good. I mean, so that ties back to the trust element, I think, because trust can come in so many flavors. My preference for trust is explainability or verifiability, because there are interesting mathematically rigorous things one can do there, right? The human factor side of trust is important, but there's just not as much rigor there as far as I can tell. So I would like a more mathematically rigorous view of these things. Yeah. And I mean, it's true that the private sector wouldn't focus on that. I can't imagine OpenAI starting a deep theory department for, they want results, right? So, yeah. That makes sense.
But I guess eventually we will still be wondering why this large language model will work, like transformers, diffusion model.
Yeah.
So what are the fundamental nature of such that this approach can give us a good solution?
Right. Yeah, that's a good point.
Yeah, I mean, following up on that, I think another aspect of that, which is, I think, important, is that not only does it allow us to explain why these models work, but then also points to things that don't work well,
Mhm.
right? I mean, if you have a theoretical understanding, then you
Right.
understand where the pitfalls are.
Yes.
Right? For example, I mean, I'm sure you've read recently about, the newer version of AlphaGo,
Mm.
which has been beaten, right, by a human, right? And
Yeah.
this is, because clearly there were pitfalls, right, with the way in which the algorithms.
Yeah,
work.
it can actually fail to fairly naive tactics.
Exactly.
Yeah.
Exactly. And so, yeah.
Yeah, and I mean, that's a good point, and that ties back to the knowledge guidance, because so the research I presented, my research was taking what you could call an explanation. When you learn this DFA, it's an explanation of the underlying dynamics. In the example of chess, it's an explanation of the tactics that led to winning chess. But they also tell you where you need to learn more. Based on those transitions in the DFA, you can say, actually, this tactic didn't work, maybe I should revisit that. So it all ties in. Explainability doesn't just give you a sense of trust, it points to where you should learn more and can be used for more data efficient learning. It's a triple threat, yeah. Yes,
So DARPA in the past has invested in the cyber grand challenge.
yes.
So do you think, will DARPA invest another language model for cyber offense and defense?
That would be exciting. That would be exciting. If you have ideas for what an interesting grand challenge would look like, we can discuss that. I've been interested in coming up with a grand challenge, but well, it's in the title. It has to be grand, right? It has to be this very big deal. And I'm not quite sure how to ground it, because in the case of foundation models for autonomy, where do you get the embodied agents, right? Who do you contact for that? I mean, I have some ideas, Boston Dynamics and some folks, but it's not so easy to start a grand challenge. Yeah.
Or maybe you online, any questions?
Oh,
Yeah, feel free to unmute if you're online. Unmute and talk.
all right. There's nothing in the chat, but if anybody wants to ask questions.
It doesn't have anything. But
I have a general question.
Yeah.
What is the I2O office that you work in, the Innovation Information Office? What do they do? What they're
It's mostly AI and cybersecurity. There's a smidge of quantum that somehow got brought in, but basically DARPA is split into various offices. Each office focuses on a different thing. We have a fundamental research office called DSO. They do a lot of fundamental physics. Most of the quantum is also there. We have MTO, which does a lot of the microelectronics, emerging architectures, things like that. We have BTO, which does biotechnology. And then I2O is the techie office, so AI and cybersecurity. Yeah. And then we have some other offices that do more applied stuff closer to the real world. Yeah. All right.
any other question? If none, then let's give another round of applause.
Yeah, I appreciate it. I really like to assist with your microphone. Usually you have a microphone and you're scared to put it close to your mouth, too far away from you.